Hello everyone, this is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today, I'm going to discuss about different biasing circuits of the transistor. So while coming to the contents, here I'm going to discuss about what is meant by biasing and what is the need for biasing and what are the different types of biasing circuits we are going to utilize for providing the bias for the transistor. So in that, I'm going for, first of all, what is meant by biasing. So biasing is nothing but generally, in order to check the performance or operation of any particular device, we require the biasing here. Okay, in order to provide the proper biasing, we need to set the correct voltage and current levels for the device so that we can able to get the proper output across the output of the device. So in the case of transistor, so biasing is nothing but it is the process of setting the transistor's DC operating voltage or current conditions to correct level so that AC input signal can be amplified correctly by the transistor. So in order to get the amplification process, we are setting the AC and we are setting the desired DC voltage and current levels for the transistor. That indicates the biasing of the transistor. Generally, transistor we are utilizing for the switching operation as well as amplification operation. So in order to make it as the amplifier, we have to provide the biasing for the transistor in the active region of operation. That is nothing but the emitter based junction should be forward biased as well as collector based junction should be reverse biased in order to get the active region of the operation. So we have to set the proper DC voltage and current levels in order to achieve the faithful amplification from the transistor. Okay, so how we can get this proper DC values means if we provide the proper DC voltage, from that we can able to get the base current and from that we will get the proper collector current. Okay, so if we get the proper collector current means we can able to set the proper operating point for the transistor so that it will provide the faithful amplification. So and also we have to choose the collector resistance we have to choose in order to provide the collector to emitter voltage 0.5 volts in the case of germanium type of transistors and 1 volt for the silicon type of transistors. So these are the requirement in order to provide the active region of operation as well as amplification process for the transistor. So actually what is the need for biasing here? If we apply very small signal to the transistor, it cannot be amplified. So in order to utilize the transistor in active region or for amplification application, we have to provide two conditions for the transistor. That is, the input voltage should be greater than the cut-in voltage of the transistor, and also we need to operate the transistor in the active region of operation. Then only we can able to achieve the faithful amplification from the transistor. Okay, so the DC voltages or currents are given to the transistor so that it will operate in the active region. So once it is operated in the active region, then we have to superimpose the AC signals to be amplified. Okay, so that we can able to provide the proper biasing. So this providing of the proper DC voltages and currents throughout the AC signal or AC cycle, then only we can able to say the proper DC biasing is achieved. That is nothing but we are providing the bias, we are providing the external supply voltage in order to provide the biasing for the transistor. We are not providing any external signal for biasing here. Biasing for to activate the device. Then after biasing or after providing the DC voltages and currents, then we need to apply the weak signal. Then we can observe the amplified output across the output of the transistor. So our required condition here it is to we have to make the proper DC biasing, and we need to operate the transistor in the active region of operation for faithful amplification. So to achieve all these, we are having different transistor biasing circuits. So before going to the different transistor biasing circuits, first of all, why we are using this particular biasing circuits that are used to set the proper operating point of the transistor. So what is mean by operating point here? So operating point is nothing but where the DC load line crossing the characteristics of the amplifier or transistor. That crossing point we can call it as the operating point. So that operating point is the combination of the voltage and current, that may be input or output depending upon which type of operating point we are going to take. So to set, if we set the proper operating point, we can able to utilize our transistor in the form of amplifier as well as switch. Suppose if we set the operating point at the cutoff region of the transistor, then we can utilize our transistor as off switch. And similarly, if we set the operating point in the saturation region, then we can say the transistor is acts like a closed switch. And if we place the operating point in the active region of operation, then we can utilize our transistor as an amplifier. So these operating points are of two types. One is input operating point and one is output operating point. So to find the input operating point, I am considering the common emitter amplifier here with active region of operation. Okay, I am taking the common emitter amplifier in the active region. That is nothing but base emitter junction is forward biased and collector to base junction is reverse biased. So to find the input operating point, I am applying KVL in the input side of the circuit, so that I will get VBB minus IBRB minus VB is equal to 0. So to find the operating point across the input side, we have to find the input voltage as well as input current. So from this equation, we can find the input voltage and input current here. So in this case, the resistance RB as well as base to emitter voltage of the transistor are fixed. Okay, so that we can change the VBB as well as IB values here. Suppose if VB is equal to 0, VBB is fixed here, VBB is fixed and RB is fixed. So we need to change the VBE and IB values. So if we want to calculate the IB value from this equation, so that I have to make VB as 0 in this particular equation 1. If VB equal to 0 here means we will get it as IB equal to VBB by RB. So that is the input current. And similarly, to find the base to emitter voltage, I have to substitute IB equal to 0 in the equation 1. If we substitute IB equal to 0 in equation 1, we will be getting here it as VB equal to VBB, that is supply voltage. So these P1 and P2 are the two coordinates of the operating point. That is nothing but P1 is nothing but 0 comma VBB by RB, that is current. P2 is nothing but VBB comma 0, that is input voltage. This is input current and this is input voltage. So the total operating point is VBB comma VBB by RB, that is nothing but VBE and IB. Okay, so these points we need to indicate on the input characteristics of the common emitter configuration. So in the case of input characteristics of common emitter configuration, we are having input voltage is VBE and the input current is IB. So we are taking VBE versus IB so that we will get the curve like this, that is nothing but the base emitter junction, the first junction is forward biased, so that the characteristics we will get it as forward biased characteristics of the diode. So same thing we have got in the input characteristics of the CE amplifier. So these 2 points here, VBE equal to VBB I am indicating here. And similarly, IB equal to VBB by R. So if we join these 2 points, then we will get here it as DC load line. So where this particular DC load line is crossing this input characteristics of the CE amplifier, then this particular point we can call it as the operating point or input operating point. Okay. And similarly, we have to find the output operating point. So to find the output operating point, we need to apply the KVL to the output circuit of the CE amplifier. So in this case, the current direction is in this direction. So that is VCC minus drop across RC resistance, that is ICRC, minus this voltage is VC. So VCC minus ICRC minus VC equal to 0. Take it as the second equation. So to find the operating point in the output region, we have to find the output current as well as output voltage. For that, here VCC as well as RC values are fixed so that we can able to vary the VC voltage or collector current. Suppose if I am making VC voltage as 0 in the second equation, then I will get my IC current as VCC by RC. And similarly, if I make IC equal to 0 in the second equation, then I will get it as VC equal to VCC. So the operating point is VCC comma VCC by RC. So this operating point we have to indicate on the output characteristics of the CE amplifier. So how we can get the output characteristics of the CE amplifier? That is output voltage versus output current, that is VC versus IC when IB is constant. So these are different constant values of IB. We will get here it as collector current. Okay. So these 2 points we have to indicate here, VC equal to VCC and IC equal to VCC by RC. If we join these 2 points, then we will get the DC load line. And wherever this point crossing the output characteristics of the transistor, then we can say that point is the operating point or quiescent point. So in this way we can find 2 types of operating points in the case of transistor. Why? Because it is a 2-port network. It is having 2 ports, input port as well as output ports. So that's why we are having 2 characteristics. So that's why we are having 2 operating points. Okay. So once we are fixing the operating point, it should not change in order to get the faithful amplification. But because of changes in the collector current, the operating point is also varying here. So how this collector current is varying here? The collector current is varying with 2 reasons here. One is if the change in beta, that is current amplification factor in the common emitter configuration, if any variations in the beta, the current variation we can expect in the collector current. So if why? Because beta is nothing but IC by IB here. So from this we can write IC equal to beta IB. If beta is increases, IC value will increase. If beta is decreases, IC value is also decreases. So the collector current value is depending upon the beta variations here. And one more reason here it is, if the temperature is varying, the collector current is also varying. That we can observe from the collector equation of the common emitter configuration, that is beta IB plus beta plus 1 into ICB. We can also write it as IC equal to beta IB plus ICE. Both are same. So in this case, if the temperature is increases, the reverse saturation current is also increasing. This total value will increase. If this total value is increasing, means the collector current is also increasing here. So if the temperature is increasing, the collector current is also increasing. If beta is increasing, the collector current is also increasing. So if any variations in the beta as well as temperature, there is a variation in the collector current. So But for faithful amplification, we need to maintain the stable operating point. That is nothing but stable collector current. Here VC is nothing but VCC voltage, that is fixed. See, the operating point coordinates are VCE and IC here. VCE is nothing but applied voltage, VCC, that is fixed. But the IC only varying here. So we have to make it as stable or constant value. So in order to make it a stable and proper IC or without variations, we are utilizing different biasing circuits for the amplifier to get proper operating point. So these are the different biasing circuits to maintain the proper operating point and to get more stability from the circuit or amplifier. So in that we are having fixed base bias or fixed resistance bias circuit and collector feedback bias, dual feedback bias and fixed bias with emitter resistor, emitter bias and emitter feedback bias and voltage divider bias. So these are the different biasing techniques we are using to provide the proper operating point to get the faithful amplification from the transistor. So in that, first I am going with the fixed base or fixed bias circuit here. Further, in all the biasing circuits, I am taking the common emitter configuration. So emitter terminal is grounded here, or else it acts like a common terminal between the base and collector here. So fixed base bias is nothing but we are providing the base resistor. So this is your normal common emitter amplifier. For that we are adding the base resistor. Okay, and to see the operating point variation, first of all we have to find the coordinates of the operating point, that is IC comma VC. Why always I am talking about the output operating point, why not input operating point? Means amplification, how much we are getting we can see across the output circuit. So that's why I am concentrating on the output operating point in all the biasing circuits. So to find the operating point, I need to find IC and VCE values. So to find the IC value, first of all, we need to calculate the base current in the circuit. So if we need the base current, we can able to find the collector current. So to find the base current, first of all, I am applying KVL to the input loop here. I am applying KVL to this input loop so that I will get VCC minus IBRP minus VB equal to 0. So from this, IB equal to VCC minus VB by RB. So base current is this much. So in this case, VCC is fixed, VB is fixed and RB is also fixed here. So if we provide the fixed base resistance value, we will get the fixed base current. So if we get the fixed base current means we will get the proper collector current also without any variations. Because of that reason, we are calling it as fixed base bias or fixed resistance bias circuit because of providing the fixed resistance value. Because of providing the fixed resistance value, there is no variations in the collector. Okay, so here we know that IC equal to beta IB. Okay, and substitute the IB value here, that is beta into VCC minus IB RB minus VB. This one take it as the first equation, and here VB equal to 0.7 volts for silicon and 0.3 volts for germanium type of circuits. And to find the VCE voltage, now we got the IC value, and to find the VCE voltage, apply KVL to the output loop of the CE configuration. That is VCC minus ICRC minus VCE is equal to 0. And from this we can write VCE equal to VCC minus ICRC. So VCE value we got here it as VCC minus ICRC. Okay, so here VCE value is fixed. Okay, VCC minus ICRC we are taking, but IC value is varying with the beta here. If the beta is varying means IC value is also varying in this case. Okay, and in this particular type of biasing circuit, the stability factor is beta plus 1, that is very high. So if the stability factor is very high means we will not get stability across the output. So it is having poor stability, so that we are not going to utilize this particular fixed bias circuit for the amplification purpose. So generally we will use this fixed bias circuit for the switching operation or automatic gain control operations only. So this is the drawback of the fixed base bias. It is having high stability factor and less stability. So next we'll go with the next kind of feedback biasing circuit, that is collector feedback bias. So what is the difference between the previous circuit and this circuit means? In the previous circuit we have added the resistor to the base. Okay, from the supply to the base. But here collector feedback bias means we are providing the feedback from the collector to base through the resistance RB here. Okay, we are providing the biasing from collector to base through RB resistance. So in this particular case, if we find the VB voltage, we will get it as VC minus drop across RB, that is VC minus IB RB. That is the base voltage. And similarly, if we find the collector voltage VC, that is VCC minus IC plus IB into RC. Okay, so these two are the voltages which are flowing in this particular configuration. Okay, so in this case, suppose if the collector current is increasing here, the collector current is increasing means there is a decrease in collector voltage. Sorry, if there is any increment in this magnitude means the VC voltage will decrease. So once the VC is decreasing means, okay, the base current will also decrease here. Here the voltage providing here it is decreasing means the IB current is also decreasing here. So once the IB current is decreasing means automatically the IC current will also decrease. Why? Because IC equal to beta IB. If IB is reducing means automatically IC value also reducing here. So in this type of biasing circuits, the incrementing the collector current due to biasing or due to VC is reduced by decrement in the base current. Okay, increment of the VC is increasing the collector current, but decreasing the IB is decreasing the IC current. So that increment is compensated by this decrement, so that we can get the constant collector current to achieve the proper operating point and to get the faithful amplification. Okay, so here VB is nothing but the base to emitter voltage, IC is nothing but beta IB, and that is almost equal to the emitter current. Why? Because there is no resistor present in the emitter to provide the drop. So that's why I is approximately equal to the IC current here. So while coming to the stability factor is almost less than beta plus 1 in this particular collector feedback bias, so that we will achieve better stability than the fixed bias circuit. And next kind of biasing circuit is dual feedback bias circuit. That is nothing but in the previous circuit we provided the resistance from collector to base. Along with this we are also providing one more resistor, that is R1, from base to emitter. So if we add this particular resistance value, any increment is there or not, we have to see here. So if we take the collector feedback bias, the stability factor is reduced and we achieved the more stability compared to the fixed bias circuit. So in this case also, any variations or increment in the IC is reduced by this I1 current here. Okay, I1 as well as IB current here. So okay, if IC is increasing means the VC value is decreases here. If the VC value is decreasing means the IB plus I1 value will decrease. So if IB plus I1 value is decreasing means automatically the collector current will decrease here. So this increment is compensated with this particular decrement, so that we can able to get the stability, more stability here, and we can get more stable collector current to provide the proper operating point for the transistor. So dual feedback bias is more stable than the collector feedback bias as well as fixed bias circuits. And next one is the fixed bias with emitter resistor. That is nothing but what is the basic difference between the fixed bias as well as emitter bias with emitter resistor. Fixed bias with emitter resistor means, first of all, we have to consider the fixed bias circuit. This one is the fixed bias circuit. For that, we have to add an additional resistor, that is RE. Then it becomes the fixed bias with emitter resistor. Fixed bias with emitter resistor. So now we will see what is the effect of this emitter resistor in this particular biasing circuit. So to see the effect of this emitter resistor, first of all, we have to find the coordinates of the operating point. That is, what is IC value and what is VCE value at operating point. To find that, again, we need to apply the KVL to the input side of this circuit. Then we will get VCC minus IBRB minus VBE minus IERE is equal to 0. So we can find IB from this particular first equation, and after finding the IB we can able to find the IC. Why? Because IE equal to IC plus IB. Okay. So here in the place of IC we can replace it with beta IB, and here it is equal to IE equal to beta IB plus IB, that is nothing but beta plus 1 into IB. So now substitute 2 in first equation, that is nothing but this IE value substitute here. Then we will get it as VCC minus IBRB minus VBE minus of beta plus 1 into IBRE equal to 0. And from this, if we take IB common, we will get it as VCC minus IB into RB plus beta plus 1 into RE minus VB equal to 0. And from this, IB equal to VCC minus VBE divided by RB plus beta plus 1 into RE. So this is the base current, but we require the collector current here. But we know here IC equal to beta IB. So substitute this IB value here. Then we will get it as IC equal to beta into VCC minus VBE divided by RB plus beta plus 1 into R. So this is the collector current, or one of the coordinate of the operating point. And similarly, we need to find the next coordinate, that is VC voltage. For that, apply KVL to the output loop for this particular circuit. That is VCC minus ICRC minus VCE minus IE into RE is equal to 0. So here IE is approximately equal to IC. Why? Because base current is very less. So that we can replace IE with IC in this sixth equation. So that we will get VCC minus IC of RC plus RE minus VC equal to 0. So VC equal to VCC minus IC into RC plus RE. So this is the VCE voltage. So we got both the IC current as well as VCE voltage, and if you observe here again IC consists of beta. If any variations in beta, the collector current will vary here, but because of using this RE we are not getting that variations. How we will see? Actually once the operating point is fixed, it should not change for faithful amplification, but IC is changing means the operating point is also changing. Why? Because IC is the one of the coordinate of the operating point. So here in this particular circuit, IC is changes due to two things. One is if the temperature is increases, the collector current is increases. Why? Because IC is nothing but beta IB plus beta plus 1 into ICBO in the case of common emitter configuration. So if any variations in temperature, there is similar variations in the reverse saturation current. So once the reverse saturation current is changing means the collector current is also changing. And And also, if you take the second equation, that is, if IB is decreasing here means the collector current will increase here. So this increment will be compensated with this particular decrement in the collector current. So this is achieved by using the emitter resistor here. Because of this drop, the collector current is reducing here, that is compensating here. The increment in the collector current is compensated by decrementing due to emitter resistor. Okay, and the second reason is if beta is changing means collector current is also changing. Why? Because we got the collector equation is this much from this fixed bias with emitter based resistor. We got IC equal to beta into VCC minus VBE by RB plus beta plus 1 into R. So here beta plus 1 is approximately equal to beta. Why? Because beta value is very high compared to the 1. Okay. So here I am replacing beta plus 1 is equal to beta. So here this beta RE value is very high compared to the base resistance. So that we can neglect this. So that we will get it as IC equal to beta into VCC minus VBE by beta RE. So in this case both the betas will get cancelled in the numerator and denominator. So now our collector current is independent of the beta here. So that we can get the stable collector current, so that from that we can able to get the stable operating point in order to get the faithful amplification. So in both the cases, by using the emitter resistor, the collector current variations are nullifying, as well as similarly because of utilizing this RE resistance, the collector current variations are nullifying here. So that is the advantage of adding extra emitter resistor in the biasing circuit to achieve the proper operating point, and from that achieve the proper amplification from the circuit. And because of adding the emitter resistor, we are also having the disadvantage. What is that means? Here, to nullify the variations of the collector current, we have to maintain the beta RE value should be very greater than the base resistance value. Okay, so in most of the transistor, we don't know the value of beta. It may vary here. Suppose if you take same two similar transistors also, it is having same properties or same characteristics, but even though the beta value may different here, even though if you take the similar transistors. So that's why to achieve this condition, we have to make the emitter resistance should be very large or base resistance should be very less. Suppose if we increase the emitter resistance is very high, means we have to keep the collector to emitter voltage also very high. If we make like this, it will increase the cost of this system. Or else, if we decrease the base resistance value, the reverse biasing of the collector base junction will be reduced here. So that will affect the biasing of the total overall circuit. So it is providing the advantage, and at the same time it is also providing one of the disadvantage, that is increasing the cost as well as decreasing the reverse biasing condition of the circuit. And the next kind of biasing circuit is emitter bias circuit. That is nothing but we are adding extra resistor in the emitter along with the base here. So in this case, before discussing the current variations as well as operating point, first of all we have to know the different voltages and currents in the circuit. So this VE voltage we can calculate from minus VEE plus IARE, and VC is nothing but VCC minus ICRC, and VB is nothing but VBE plus V drop across emitter also, and IC is nothing but beta IB, and it is almost equal to emitter current. Okay, so here if we observe, it is having two types of polarity biasing voltages, that is VCC and VE. Both are providing the biasing voltages but in opposite polarity. So in this kind of biasing circuits, the collector current is independent of the beta here. Okay, and we have to choose the VB by choosing RE value should be far greater than RB by beta, and VE should be far greater than VB. If we maintain these two conditions, then we can able to achieve IC is independent of beta. So if IC is independent of beta means we will get the stable operating point, we will achieve the less stability factor. So if the stability factor is less means the stability will be more, so that we will get proper faithful amplification. And next one is emitter feedback bias. That is nothing but for the collector to base feedback bias, we are adding one additional resistor R1 from emitter to base. So this is the emitter feedback bias circuit here. So to find the VC voltage here, we have to take, here it is VCC supply voltage, VCC minus IC plus IRB into RC. And similarly, to find V, we have to take IE into R. So similarly, we can find all the voltages here. And in this particular case, if the temperature is increases because of common emitter configuration, the temperature is increases, the reverse saturation current will increase. Once the reverse saturation current is increasing means the collector current will increase. So once the collector current is increasing here means automatically the emitter current will also increase here. So once the emitter current is increasing means the drop across the emitter resistor will also increase. Okay. So once the drop across emitter resistor is increasing means the VC voltage will decrease here. So once the VC voltage is decreasing means automatically the base current will decrease. So once the base current is decreasing means the collector current will also decrease. So it will come to original value. So because of the temperature, the collector current is increasing here. But again, it is reduced to same position. Okay. So that increment in IC is compensated. Again, it is decrementing so that we will get the more stability and we will get faithful amplification without any distortion across the output. And next one is the voltage divider biasing circuit. So here we are taking again common emitter configuration. We are splitting the base resistance into two resistors R1 and R2 here, and the collector resistor and emitter resistors are same here. For all the terminals we are providing the resistance here. For the collector terminal RC resistance, for the emitter terminal RE resistance. So RB resistance we are dividing into R1 and R2. So in this way also we are trying to provide the biasing, whether we are achieving the proper stability or not, we will see this. So to find the operating point or coordinates of the operating point, that is IC and VC, we have to take the Thevenin's equivalent circuit of this one. So what is mean by the Thevenin's equivalent circuit? So what is mean by the Thevenin's theorem and Thevenin's equivalent circuit? For example, I am considering this particular circuit here, network. So from this, we need to find the Thevenin's voltage as well as Thevenin's resistance in order to make the Thevenin's equivalent circuit here. So how to find the Thevenin's voltage here? So Thevenin's voltage we can find from this AB terminals from here. Okay, Thevenin's voltage is open circuit voltage at terminals AB. Open circuit voltage at terminals AB. Okay, how to find the Thevenin's resistance? So Thevenin's resistance also we can see from this AB terminals when means with all voltage sources are short circuited and all the current sources are open circuited in the given network, then we can able to find the Thevenin's equivalent resistance. So if we apply these two conditions to find the Thevenin's voltage and Thevenin's resistance, we can replace this network as Thevenin's equivalent network with single resistance and single voltage. So this is Thevenin's equivalent circuit with Thevenin's equivalent voltage and Thevenin's equivalent resistance. So this particular same Thevenin's equivalent circuit we are going to use in the voltage divider biasing circuit. So this is our voltage divider biasing circuit. If we apply the Thevenin's theorems to this, we will get this particular circuit. Okay, we are replacing this R1, R2 resistances with the Thevenin's equivalent resistance R Thevenin's, that is equal to R1 parallel with R2, that is equal to R1 into R2 by R1 plus R2, this one. And the total voltages in the circuit we are replacing with the Thevenin's equivalent voltage, that is equal to VTH. How we can calculate means R2 divided by R1 plus R2 into supply voltage VCC. By using voltage division rule, we can able to find the Thevenin's voltage. So this R Thevenin's and V Thevenin's we are going to find the, by using this R Thevenin's and V Thevenin's we are going to find the IC and VCE values. So for that, to find the collector current, first of all we need to find the base current. So to find the base current, first of all we need to apply the KVL to this input loop. So in this loop, apply the KVL to this loop, we will get it as V Thevenin's minus IB into R Thevenin's, okay, minus VBE minus drop across RE, that is IARE, is equal to 0. Okay. So if we find the IB from this, we can find the IC. And again we know the emitter current is equal to the sum of the collector current as well as the base current. So IE equal to, here I am replacing IC with beta IB. So I will get it as IE equal to beta IB plus IB, that is equal to beta plus 1 into IB. So substitute this IE value in the first equation. So we will get it as V Thevenin's minus IB R Thevenin's minus VBE minus of beta plus 1 into IB into RE equal to 0. And from this take IB common. So if we take IB common, we will get it as V Thevenin's minus IB of R Thevenin's plus beta plus 1 into RE minus VB. So to find IB, we will get it as V Thevenin's minus VBE divided by R Thevenin's plus beta plus 1 into RE. And we know already IC equal to beta IB. So now substitute IB value here, this value. We will get it as IC value, collector current, that is one of the coordinate of the operating point. And similarly, to find the VCE voltage, apply KVL to the output loop. We will get it as VCC minus IC, RC minus VCE minus IE into RE is equal to 0. So here emitter current is approximately equal to the collector current. So I am replacing emitter current with the collector current in this equation, so that we will get it as VCC minus IC into RC plus RE minus VC equal to 0. If we simplify this, we will get it as collector to emitter voltage as VCC minus IC into RC plus RE. So this is the collector to emitter voltage, that is the one of the coordinate of the operating point. So what is the advantage of this voltage divider biasing means? R Thevenin's is the combination of the R1 and R2. So to make IC is independent of beta, we have to maintain this R Thevenin's as very much less than beta plus 1 into RE. If you maintain like this, we will get the stable collector current, so that stable operating point, and we will get faithful amplification. And in this particular voltage divider biasing circuit, the stability factor is 1, so that we can achieve more stability. So among all the biasing circuits, voltage divider biasing is very useful, and we will get the amplified signal without any clipping or without any distortion if we use the voltage divider biasing circuits. So the intention of any biasing circuit is to provide the proper DC levels to the circuit in order to amplify the applied input signal. So to achieve the amplification, we have to operate the transistor in the active region as well as we have to provide the proper DC voltages. So till now we have discussed the different biasing circuits to achieve the proper operating point and to achieve the stability and without variation of the collector current. So operating point is varying with the collector current here, not with the collector to emitter voltage. Why? Because that is the supply voltage and that value is fixed. But the variation is only due to the collector current. So in order to compensate the variations of the collector current, we are using the different biasing circuits here. So each and every biasing circuit is having its own advantages and disadvantages, but depends upon our requirement, we can choose any particular biasing circuit. But I can say among all the biasing circuits, voltage divider biasing circuit is the best one to provide the proper stability and faithful amplification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.